5 seconds to the contest. Yeah, starting now. Okay, given an integer k, print a string that is concatenation of the first k letters. And if I, okay. Submit m participants, m problems for an integer I between 1 and n, an integer j. Participant I can solve the j problem if it's 0 and cannot solve x. The participant must be in pairs. Print a number of ways to form a pair of participants who can solve collectively all m problems. So you have some matrix, you need to print to solve the m problems. You will have to go through all of the subsets. Oh no, not only pairs, okay, only pairs. I thought, yeah, nothing. Just a simple I need to close out the window in a moment. If C is X map IJ is true, and then I need to close the window, it's too much noise. What? Oh, is it reversely? Yes, it's quite wet. Okay, let's see. You're given a string consists of lowercase, which letters this and that is guaranteed even number of these. Let 2k be the number of apostrophes in C for each of this, the character enclosed. Your test to replace this Yes, that is, as it is not an enclosed character with dot, print the resulting. Yes, so just a simple task of having the balance, keeping track of the balance. This will do. Oh, I'm not outing this. We're given a simple undirected graph. We print the number of pairs UV and both of the this satisfies both of the following conditions accepted on the first three problems. Graph G does not have an edge connecting U, V, and V. So, okay, so there's not a direct connection. Adding an edge connecting vertex U and V in the graph results in a bipartite graph. So there's no connection between U and V, and when I add an edge, it's still bipartite. So the problem, okay, so the graph has to be bipartite by the beginning. So we can count. Just need to count how many are on the one side and how many are on the other side that are not, yeah, well, they're not neighbors to this guy. Okay, I mean, why am I test casing here? Okay, there's no test cases. Int n and m, and then there's vector adjacency list. Oh, what? No. Just read UV. Okay, and then we say color on the one side and color on the other side. Vector So in the BFS I will say BFS.push 0. Okay, I will say black plus color 0 is 0, and then I will say okay, for each vertex in the adjacency list to the top vertex, if color at v is -1, then color at v is color at top like this. BFS.push there, and now we say, okay, so instead of black and white I will say vector int count count 0 plus plus. I'll say count at color at v plus plus, else if color at v is not color at top this, then cout 0 and return. So there's no pairs, that is not bipartite to begin with. Okay, so we visit all the pairs, and then we say for each node we just assert that you're given simple undirected graph, but it doesn't mean that it's connected, right? So if it's not connected, I will okay, so if it's not connected, I will do this for all of these. I will create a if color at I is not -1, and this should be an integer as well. Continue. Otherwise, push e, say color at e is 0, count at this color plus plus. But now we want count by components, not by connections. So we want to count by components. So I want count push back this vector count dot back this is I plus plus, and count dot back this is plus plus. So we push a new component, we make this, then we go through all of the components and say, okay, so I cannot connect it only with this, I can connect it with everybody else, but not with the component that has the same color with this, and not with the edges. So int current answer is okay with everybody else except me, and current answer is also cannot connect with the adjacency list, and also it cannot connect with the component that has the same color. So also in my component, what is your component here? So component at I equals component dot size minus 1, and here I put in like, yeah, and now I cannot have in the component the count of my component, which is different than which is the same with my color. There's n, there's this component at I is this. Let's see, where do we have overflows? Component at top is component size minus 1. Color at V is color at top, shift by 1. Count back at color at I, back minus justify that size minus count at component of I, component of I. So this finds out that it's not a bipartite graph. Color at V plus color at top. So color at top is 0. Count of the component of I and color of I. Component of I is 4. Oh no, not component size, count that size. 2, 9, that's correct. Let me just wait for the judge. Accepted. Let's see how the standings doing. Okay, we are 154th place, which is nice. Okay, E. Choose n balls. Okay, the box contains n balls with this integer written on it, AI. Okay, while the box has 2 or more balls remaining, Takahashi will repeat the following. We'll choose 2 balls arbitrarily, then get a score equal to the remainder when this is divided by m. Okay, so we have some huge modulo and we get this score where x and I are the integers of the 2 balls. Finally choose one of the two balls arbitrarily and eat it. The other one return to the box. Print the maximum possible total score the Kakashi will get. This is heavy mathematical problem, but maximum possible total score. So because arbitrarily we're choosing balls, can we for each pair calculate what is its remainder modulo this huge number? And what I don't understand, what's the... Okay, we choose two balls arbitrarily. Maximum possible total score. Oh, so he wants to do this repeatedly and still gain. Okay, so something like Floyd partial, right? But okay, so let me open up Notepad. CP algorithms. Okay, so what's the idea? So okay, for each pair we know the score, x to the y and y to the x, right? We know the score modulo m, and then we say what is the best continuation. It's like the same having Floyd partial. Is it... So if I have nodes like this is the score here and the score here, and you just need to travel through the node. So it's clear Floyd partial or not so easy. I'll try to implement it just to quickly see, because it's quick enough implementation and I don't need to go through all of the possible. So I have to have a binary exponentiation function here where I have some modulo operator. Okay, so this is binary. Now we say the following. We say, okay, we have some integers. dp of int 0 the between element was here, if I'm not mistaken. Haven't called Floyd partial in a while. So dp of, but now the trick is here that, okay, I get the score of one of the elements, I get the score of the other element. They are, yes, so they're commutative scores, but they're not. Is it Floyd partial? Like Pij is the maximum of dp of ij and then the idea of this, so dp of, so the problem is like, okay, ai, aj, through this, so dp of what I have. So from I to the k number, from I to the k number, where k is the last. So, right. If k is the middle number, if a of k is the middle number, a of so it's like dp of I of k plus this. I will do calculate of so yeah, the score could be a long. The score could be a long. I'll just convert everything to long. So okay, I go for I to k. I have the last, and then like, can I do kj here? And then plus dp of, no, I need like 2 in bit, so I through k somehow. Now let's think about this. Okay, so we have all the pairs, right? I want to arrange the pairs such that when it's actually consecutive. Okay, so let's do this. So if I have one pair x to the, so if I have one pair x to the epsilon to the x, then the next, this is modulo. Is the same as I'm saying this modulo this plus this modulo this, no? Isn't it the same? Wait, this is the same, but then when I do this pair, one of these will fall down, and the other can again be used. So a greedy approach, I would think, is to find what is the biggest. Oh, actually not. What is the biggest through this module, like that, and then combine this biggest with every other else number, and this will give but it changes here, so it's not okay, so it's not x always here, it's here, depends on this. So okay, so what we have here is this, then you add on this. Let's say this is okay here, this y is okay, so you add y to some z plus z to the y, right? Again, module. All right, so I don't care about really the module here, because the module I can get out. I care about what is the best sequence that I can create such that it has the biggest power. But actually this module is kinda important somehow. If I'm ending at y and I have this power to here, I can add whatever I haven't added here. But what I'm saying with the Floyd-Warshall is, I'm saying if I have some path from I to j, can I add in between somehow y? So this is x to z, I have some path from x to z. Can I add somehow in between y so that I have some path? So yeah, so from x to some other number here, and from some other number to z, if I add in bit, or I directly add it from x to y, so I calculate this and then I do k to j. Should this work? Oh no. So, and calculation is done by saying binary a to the I, binary this, put this in this module, plus binary this module, get everything according to module, return. And now we want to take any path from I to j. I'm definitely overshooting somehow. Take the first ball, the first and third balls, then eat the first and return the third to the box. How are the standings looking? Bad, 280. Okay, so what's wrong with here? I to J. K has to be outside the loop because we go. So I and J cannot be equal as far as I know. But then they can't repeat is the problem. And like I should be bigger than K and J should be bigger than K or something. Because like if I have, because it's the maximum possible score. It's the other way around. Like K could this is not too well. So K is the thing that connects dpi to K and dp K k to j. But then the trick is, how does k influence here? It doesn't, it's, no, we can't do that. Like, I don't know, like if there would be two more parameters here where I can connect k on both sides, then I can, yes, I can say that, okay, x through k has a bigger, x through k to z has a bigger thing than this path here. So for each pair, we need to, okay, if I put k here, I need to search. Let's say I put k to this and this here. This means that whatever I had previously is now only through here. So if I had all of n q and to the fourth, this will work. A second, brute force this, and this. But what if I say, okay, I don't care about this, I care about only the three components here. I care about x, but still it's n to the fourth. If I cared about, no, like, I can't, I have to have a path through here. So this says, okay, I'm at x, I throw away x and I go here, and then I go here, and then I go here. So I have a complete graph. I have a complete graph, and I want to, in this graph, I want to find a path that visits every vertex, and so it's not a, it's a Hamiltonian path, or what? That visits every vertex, and then in an order that will be the most, starting at any vertex, I can visit any other vertex in an order that is the most. So let's rethink the DP. Okay, so what if I had a DP where no, I have to have like Floyd-Warshall DP. Floyd-Warshall it. Like, it's not the longest. So if it doesn't have a positive, no, but we have to visit all of the vertices only once. So let's say another thing. Let's say, okay, so we have some sequence. Where can I put this vertex, this x vertex, such that when I put this x vertex, what will happen? What will be my contribution here? My contribution will be x to the, so it would be y to the x plus x to the y plus this module plus x to the z plus z to the x. This will be my contribution. So what I get is I get this and this by putting the vertex in between them. So in between I get x to the y and x to the z. So actually I'm putting k between these two, so I think I should get k to the j and k to the I modulo this. I don't know if this should actually... Not sure about this. Seal the correct result as the... How is this not a very big number? 100 times... Yeah, okay, so it makes sense that this is not a big number here, because we have... So y to the k and k to the j. Here k and j, here they're not... Yeah, so what you are doing here is you're adding x here. But this is not modulo. So you're adding this contribution to both of these. But this is not modulo. You need to remember which is the last one to be added with x. Modulo that plus whatever this guy is to the x. Modulo that. Yes, it's not like this. It's I to the k power with k to the I power and k to the j power plus k to the k to j to the k power. And then there's modulo, but even that it won't work because because you are adding twice. We're saying we add to the I, we add this, yeah, but we can repeat it. We have to find another DP. Okay, let's go. Let's see F union of two sets. It's an interactive problem. You and the judge will follow the procedure. Phase 1, the judge gives you an integer n, you print an integer m between this. You also print m pairs. Okay. The judge gives you an integer q. You and the judge repeat the following q times. The judge gives you two integers L and R as a query. You respond with two integers A and B between 1 and m. So there's an integer n, there's an integer m, which has these. Okay. You respond with two integers A and B between 1 and m inclusive, possibly A equals B. Here A and B must satisfy the condition below, otherwise your submission will be judged incorrect. The union of the set of LA to RA and the set of this equals the set of so these integers you have to the union of the set LA to RA and some other interval. Oh, so you have to construct intervals such that this is a nice problem. This is a nice problem actually, and I'm thinking it something has to do with 4,000 times log 2 of 4,000. Yes, exactly. It has something to do with this. So you store. So you have range minimum query in some sense, but like you store. Yeah. So you have range minimum query. Okay. So this is RMQ, exactly RMQ. Okay. I mean, it's okay that they don't have tests for this, but I have RMQ somewhere. I can just use this. In order to modify it a little bit. I have to define first what is size. Okay, so you're given some vector here, but I don't care about the vector. I will be just given like a size here. right? I don't care about this as well. I don't care this as well. So the size n. Judge gives you an integer n. Yes. So jump in place. So here are how the seconds will work. You have to print the pairs to n. So okay, void query A and B has to so it queries A and B. Okay, this is the union that is queried, right? But this here is actually so j plus the power. Okay. What is k, what is j in this RMQ here? Sparse table. Okay, whatever. So yeah, so this RMQ actually uses says jump is 1 and v. So for each power here, you have jump at this power. So you have power and you have size, right? Just a moment. So, alright, so power and size. This in places a vector of this size at the end, probably. And minus the power. So actually how we want to have like m edges where so this jump here is actually how I want to do that. You want to this jump is the power. But the power is a fixed power, right? Yes. So this power is fixed. We want to map depth to A into whatever edge we have given this. So we want to have like a map of actually, yeah, we'll have this vector of integers and we will call it jump, right? To replace this size and whatever edge is given. Now the edge here that we're going to give is, okay, we're gonna print two numbers, A and B. We're gonna print cout A and B probably, right? Do they have to be so we're gonna print A and B. We need to, okay, flush that. So when we're constructing the things here, we also want to have like edges. Not edges, but like intervals, right? And we're going to construct the intervals by saying okay, it's a bit harder to construct the intervals, but let's write this. So there's an integer n, we say rmq n, we say rmq dot print, there will be like print here function which prints the edges. Then we'll say there's qquery is given. Each query is made of lnr, and then we're gonna just rmq query lnr. Now one more thing here. RMQ query is inclusive and exclusive, so L has to be smaller. Okay. And now we say how do we generate these intervals is the problem. The problem is how do we generate them. Okay, so we need, okay, jump is actually to what edge we're going to. Okay. So how do we generate this? The first idea is if I have all of these same, so the first jump I have to push back a vector here, but the vector will be like I need to generate for each of the n, I need to generate, I'll push back a vector. Actually, can I in place back n? And then for each of these, I'll say jump at 0 at I is equal to I, and I will say intervals push, yeah, intervals push back I, right? Yeah. I will say, okay, in cout intervals dot size auto element in intervals cout element dot first plus 1 element dot second plus 1. This will print the intervals, but now here it becomes a little bit more complex. Here it becomes a little bit more complex because okay, we push now a smaller version, so for the smaller n, but all of these should push their own intervals here, something, and then we should say that this kj, if I want this kj, it's inside this interval and this interval, right? If I'm not mistaken here. Okay, I get one of the intervals which has the same, which has the smaller power in j, int interval 1. I get interval 2 has smaller power in j plus this power, right? Now I need to merge these two intervals. into a bigger interval, is this power plus this power here. I now merge this into a bigger interval, right? So I say intervals. So int L is I1 is minimum I. It's like minimum of the intervals at I1 dot first and intervals at I2 dot first. R is the maximum of these two. Then we say int LR, right? And we say jump at kj is intervals at size -1 is the last one. Okay, now this should primarily, this should work, but what? G++ F union F. And now let's say we're given 4. There are 4 numbers. Okay, so we have 8 here. We flush. Okay, let's give 4 queries, and one query will be 1 to 3. So 5 and 4. Okay, let's see. 4 and 5. Wait. This and this. Yeah, we have +1 to add here. Okay. So let's get again. It's 4. And now 4 queries, 1 and 3. So 5 and 6, 1, 2, 3, 4, 5 and 6. Okay, let's get 3 and 4. 7, 7. So 1, 2, 3, 4, 5, 6, 7. Okay, that seems correct. 1, 1. That seems correct. 2 and 4. 2 and 4 is 6 and 7. 1, 2, 3, 4, 5, 6, 7. 2 and 4. That seems correct. But yeah, it should be technically correct. We should have tested it for like huge and it's wrong answer. Oops. I will say this 4 out 4. No. Okay, let's just open up out, see what. Yeah, we're inside the mark here. We're inside 50,000. Am I not understanding here something, or it's wrong answer? So how is wrong answer? Let's submit results. Only 2 got accepted. Maybe I'm printing more than I'm allowed to. Is it possible? Okay, so the judge gives you an integer n, you give these pairs from 1 to this. I think this is okay. And then you give out, just gives you queries. You respond with only two accepted. Or something is terribly wrong. So you only respond with two integers a and b from 1 to m inclusive, but must satisfy the condition below. The union of these two sets equals this set. Okay, let's stress test. Let's test it a little bit more here. Okay, so let's give out, let's give 8. And we're going to do this. We're going to print here. Just so I know. Okay, so let's do this 8 query. Okay, I'm going to print out some very nasty here query, like 7. No, that's 7. 3, 6. Oh, whoops, no. 8. And then I have, okay, let's say 10 queries, doesn't matter. 3, 6. 18, 18. Okay, this is not correct. 3, 6 is not correct. Yes, it's not correct. Of course it's not correct. It has to be second, not first. Of course it's not correct. Okay, 8, 10 queries, 3, 6. Okay, this is not correct as well. Oh yes, it is correct. What? 18. Yeah. So it is correct. Okay, so let's do 5, 8. This is correct. Okay, let's do something that is not in the case. Let's do 6, 8, 14, and 15. Okay, let's do 2, 2. Let's do 8, 8. Let's do something that is not in the case. 1, 1, 5. Okay, this seems correct. Okay, this seems correct. You know that it's not time limit exceeded, but okay. Now we're getting somewhere. Yes. Okay, now we have 19 minutes to solve. Okay, nice, we solved F. Now we have 19 minutes to solve. Let's see how the standings are doing. Probably pretty good. Either solve E or solve EX, but let's see EX what it is. Print the number of pairs satisfying the following. The minimum from L to R plus the sum is smaller than the sum than S. I don't know. I mean, I like it. It's cool. It's a cool task, but probably solving E would make it a lot better. Just get my rating up. Okay, so solving E. E has to have some trick with the Floyd-Warshall instead of, but Hamiltonian maximum Hamiltonian path, maximum Hamiltonian path. Incomplete graphs. This is what we need. Like design linear time algorithm, maximum weight Hamiltonian path, incomplete graph where given underrated or T is given underrated. Ij is the distance in T. So like minimum. Okay, so we have all of the paths and then a maximum, like a spanning tree where like I have all of the paths. So just a moment for a second. So maximum, like maximum spanning tree. Is it possible? Is it actually maximum spanning tree or not? Take this, that is. Yeah, so it should be a maximum spanning tree, but I don't know if it was a maximum spanning tree. I can solve this in n squared times log n. Isn't this solvable in n squared times log n? This is clearly meant for cubic here. But okay, what does the spanning tree give? So if I have like these x epsilon here, the spanning tree, what does it say? It says that, okay, I take this guy here, right, and this guy, so this path, and then I take this guy here. So I remove this guy from the path, I remove this guy here. When I go here, what I say, when I take this edge here, it means that I remove this guy, but then you can't have this. So essentially you cannot have like a tree, you can only have one more further vertex, because yeah, it's like a path. You want to find a path that can just branch out one, because I can take this guy out, then so I take both of these and I eat this guy. I take both of these, I eat this guy. I take both of these, I eat this guy. Right? Then I could have potentially many other guys here that I will take with this guy, and then go my way around. So it's a maximum spanning tree. So it's a maximum spanning tree, but where you have like one path with the, so like the diameter here is like this, and then everything else on the diameter is at most one distance from the diameter. So you want maximum spanning tree with these constraints, right? Okay, so how do we do this? Yeah, here the greedy approach, well, I don't think it will work. The greedy approach, but I'm pretty sure it has to do something with Floyd-Warshall here, but I don't know how to like Floyd-Warshall Hamiltonian path. How can one utilize to find, to enumerate all single paths? No, I don't want this. Notation of the Hamiltonian path algorithm. Yeah, they're talking about some other. Gamma Ford, I mean, I don't know, the flow version for the longest path. For longest path problem. Longest Hamiltonian path. Yeah, this is why I think the tree is critical class origination penalty, special classes, programming approach. Importing is polynomial file. Region of content. Alright, so so it's a tree, it's a minimum spanning tree with like min maximum spanning tree in our case, right? But how do you know that this is one distance to the vertex? So like, okay, you take the most comparable edge. I don't know, let's try implementing something. Vector edges, you cannot take two edges, so we can do this. Edges that push back A of R, A of J, right? And then I will have like struct here, edge which has int AB, and then it has calculate a function which will cost 0 edges down back dot calculate. Cost is binary a to the b with modulo m plus binary b to the a with modulo m. And then we say bool operator cost edge e return that I have a bigger cost than him. I also want like a DSU. Then I want when I create the graph, I want the distance. So like I want to keep somehow the diameter in place. So I want to keep somehow the diameter. When I add some edge, I want to see whether the diameter changes. So that's why I actually have to go for each edge. For each edges, and then I will have to say okay, if I can add it, I say DSU. Okay, let's create a DSU. I say DSU merge element U element V, and I have to add to the answer the cost of the edge. But now here is if I can add the edge. So I can only add the edge if okay is when the DSU are not the same. So DSU are same, element UV and element V are not the same. And then there's one more constraint I need to check, is the diameter of the thing I have does it change when I add that? So how do you calculate the diameter of the tree? So okay, so you calculate the diameter. You have to keep track of the diameter of the tree though. And the problem is that this when you will merge two trees like this, and then when you want to merge them both, you won't be able to merge them both. Because the diameter of this tree might be, you have to only merge at the diameters. At like, yeah. So that's the problem why I think greedy solution won't work here. Yeah. I don't know. I mean, I don't think anything I can do. What is similar? Okay, EX is a cool problem. So like the minimum of this, print the number of pairs, LR, which the minimum plus this sum is smaller or equal to S. So can you do some trick with squared decomposition maybe? But how many? So when the minimum can only get smaller, right? And then this can only get larger. So you have a function which it gets larger by this, and you have another function which gets smaller. And now you need to say that, okay, when we compute the sum of these two functions, there will be a region we can probably ternary search where these two functions satisfy the condition so if I have a function, if I'm ending at some index I, when I go backwards and sum up these numbers, so the minimum can be like really high here and then just drops potentially down discretely, right? But then you have like the sum which always goes up, right? And then if you have some kind of, and then when you sum them up, what you get is you get something like, okay, you have this point here, the highest point, then you get some lowest point, then you get something like this. But maybe now it's is there many local minimums here? If we can prove that there's only like one local minimum, and around this point we can find this local minimum with ternary search, and around this point you can find, like, if this is S here, you can find that, okay, from starting from here, ending it here, this range here satisfies the conditions, and you can count this range. If there are multiple local minimas, so like something like that, you can have like multiple searches here. Let's say something like this. And now all of these here satisfy the condition, but okay, it's ended. Let's see the standings here. Okay, not bad, 600th place, not bad, but it took me a lot of time I spent on E for nothing, but whatever. So if there are multiple local minimums, you would somehow want to jump to them. But I don't know. I think that you cannot have this, because this will always get up or will get like this, and then if the sum is equaling, then this is actually, yeah, so like you can have probably multiple local minimums if b is always equals 0 here, and the sum always goes to a smaller point. It's probably some trick with like with windows and some interesting data structure here that will keep up this minimum, this different minimas. Or you can, when you're generating these minimas, when you add some other element here, all of these minimas will change somehow, right? And if you can just discard some of the minimas, then and create some other, or just don't create, like a minima can be created probably here. So I don't know, like something like that. Then in off n time to be keeping up with, to prove that if there was a minima here, there won't be a minima here after any iteration or something like that. I'm not sure, but whatever. Cool problems. The summary of the problems, let's just take a look at each problem, just to say here. Okay, the first problem was very simple. You had to print the first n letters of the English alphabet. Just see out character of that. That's it. Like, I'm not gonna explain anything more. Here you're asked if there are a number of pairs x and y, such that if you take these two teams, they can win all of these they can solve all of these m. So if you take these two participants, they can solve all of the m problems, right? But first I thought that like you had to have a subset, like take multiple participants, but actually it was just two participants. So you can brute force over all of the pairs and check if they can solve the m problems, right? And then that's pretty much it. You can do it with bit sets, of course, with much bigger complexity, but the problem was easy enough to just brute force it and don't care about it. Okay, then go to the next problem, right? String delimiters is just, the point here is that like you have these opening and closing apostrophes, and then in the apostrophe you don't want to change anything, but outside the apostrophe you want to change all of the commas to dots, to points. So like what you want to say is that, okay, I'm keeping a balance, and when I enter an apostrophe I change the balance, and I printed out the apostrophe. Otherwise, if it's a comma, I will see if it's inside the balance, I can't change it, but if it's outside the balance, I can. And then I print the character, and that's it. That's C. Quite a nice problem. It would have been maybe even more difficult if you would like add some like multiple like brackets to keep up the balance, not just like binary balance, but like integer balance. But of course, C should be easy enough problem, so everyone to solve it, and I believe that it's a quite nice problem, very high quality problem. I mean, quality enough problem for beginner contest. D also a quality problem. D you had to know a little bit of graph theory, but it's nothing too special. You are given a graph, a simple graph that there are some connections. Print the number of integers u and v so that you can add edge between u and v, number of pairs actually of integers u and v. So you can add edge between u and v, and it will be a bipartite graph. So it isn't guaranteed that it is connected, nor that it is bipartite. So you have to check, is it a bipartite graph? And you have to check, and you have to keep count of the colors in each component. And what I do here, I go through all of the vertices. I have for each component, I have a different like a vector count, which keeps two counts, black vertices and white vertices. And then I push like one black vertex, the first of this component. Then I go through this. If I find one component which does not satisfy the bipartiteness of the graph, it means that the whole graph is not a bipartite graph, because each component has to be a bipartite. Okay, so I just print out 0 and return. If it satisfies, I have the counts for each of the components. And I can, in this I, so this vertex I can connect it to every component n, except I cannot connect it to whatever I have adjacent to it. So whatever it is connected to it. And because we are guaranteed that the graph is bipartite, so we can imagine that vertex I somewhere here, let's say this is vertex I, it's connected to some other components. This is his component, let's say like this somehow. So yeah, something like this. So these are the nodes that I cannot connect because they're all already connected. If I have another component, I can connect I to whatever site I want here. So I can connect it either here, I can connect it either here, whatever. It will still be bipartite, right? Because they will just change colors. They will just flip. If this was 0 and this was 0 and 1, if I connect this here, this will just flip to 1 and this to 0, and it will still be bipartite. So I cannot connect I to all of the neighboring vertices, and I cannot connect I to all of the vertices that are inside of his component and has the same color. So what I'm saying, the count of the vertices that is the ith component and has the same color as I cannot do that. And just I add to the answer. Now always you need to divide the answer due to the handshake rule, that like you are counting twice for different so for each edge you're counting from this side and to this side. Just clearly divide by 2, right? Use the handshake rule. E, I won't comment on E. So the E was I couldn't solve it. It's just some another graph, interesting graph problem. I mean, it's not clearly a graph problem. It's I just reduced it to graph problem. I don't know if that's even the solution. So what I reduced E to is if I have a complete graph with some like edges, right? I have to find the minimum spanning tree such that let's make maybe one more here. So I reduced it to finding the minimum spanning tree. So its diameter, finding the minimum spanning tree. So that it's how do I draw this with, no, it's not enough. So that like if I connect it to the spanning tree, I will have like one diameter and every other node will be just one away from the diameter. So if I had like a node here, I won't be able to do this, because I would have one diameter which is like this, and the other two nodes would be like 2 away from this. And why is this? Because why I cannot do this? Because I imagine the problem as starting somewhere and taking both of these balls out, and then eating this guy and having this guy away here. And then like I can take these two out, then take this edge, eat that guy, and then when I come to here, yeah, so like I can take this edge now and this, eat this guy, then left with this, and then I can go like take these two guys, eat that, take these two guys, eat that, and now we'll be left with one. And this will be one of solutions, right? What you can do, right? But I'm just maybe somehow like DP, or I thought first that this was some kind of Floyd Warshall DP, but I'm not sure. All right, F is a really nice problem. Actually teaches you about sparse tables. So what is F asking you is you give some intervals. So you have some array of numbers from 1 to n, and you have to give at the beginning, it says what n is, you have to give some intervals in the beginning. You choose whatever intervals you want, but they have to be to 50,000, at most 50,000 intervals, right? And then what he says is he is giving you Q queries, where each query is ln(r), and then you have to show him two intervals that you gave, such that the union of those two intervals is exactly from L. Let's say this is 5 here, or whatever. Let's say 10. Let's say 2 to 10. You would want to show him this interval. This, let's say 2 to 9, 2 to 8, some interval that you gave, and then you have some other interval that you gave from 4 to 10, let's say. And these two intervals satisfy the condition that their union is 2 to 10. But you have to give the intervals in a smart way that they're covering even when n is going to 4,000. So clearly you have to give 4,000 times log 2 of 4,000 at most in number of intervals. So at most m has to be that, right? And this is exactly smaller than 50,000. It's just around 47,000 or something like that. Was not sure, but so given this, you have to be smart about the intervals. And what the sparse table does is, a sparse table first creates small intervals like this for each n. Then it creates intervals which has power of 2 like this for each n. So yeah, like that, without that interval. And then you create these intervals. But you actually wait, I'm wrong. It's like this. You create like this. So for the next step you have, I think, like this. And then you have like this. And then you have like this, the whole interval. And then if you're given L and R, you just take two intervals which cover from one point to another point, and that there will be exactly always two intervals. Or if there's like single point here, let's say this guy here, like if L is equal to 1 and R is equal to 1, let's say, then you give like this interval and this interval again. So like you repeat the interval, but it is allowed to repeat an interval because you have to if you're doing RMQ. If you're doing sparse table. So I had this implementation of the sparse table from some guy. Let's just give credit to Johan Sanemo. Let's just, sorry guys, it's just Johan Sanemo. Okay, so this is his code. I just modified it here to merge. So I just put first all of the smallest intervals, then I put for each of these, I map actually to what interval it is. For each of the jumps, I map to what interval it is. Then I merge the intervals, and I say, okay, and this jump is this interval, the last I push here. And then when I query, I just want to say, okay, take this interval, and also when you're printing out the intervals, you have to say what kind of intervals are they. Yeah, so I mean, really cool problem. And then just a few lines of code, the main block. Cool problem. I had wrong answer because of this here, second here. This had to be first. Yeah. This has to be second. So this is the end of the interval. I had it wrong. So yeah, kind of cool problem. And this is it. Thank you guys so much for watching, and I see you in the next one.